Good afternoon. Today we will discuss a new topic that is something about vector functions and limits and continuity. If you remember, we had done something about the cross product, dot product of vectors. But now we will come to the interesting part of vectors, which is vector functions. If you remember, similarly, when you were in high school, you were doing just real numbers. You were learning how to add the real vectors, the real numbers. You were learning how to multiply the real numbers. And then when you reach your higher secondary, you were doing functions. Similarly, over here, we had learned how to operate vectors. And now we will learn how to form vector functions. So first, I should specify over here, we are doing vector functions of a single scalar variable. Vector functions of a single scalar variable. I will highlight over here. So over here, what we will be having a single scalar variable. Just think of it in this way, okay? I will first give you an example and then I will define what a vector function is. Just take a look at this vector, okay? Maybe 2ti plus 3tk. Okay, so this one, it will be a vector function of a single variable t. Okay, it is an expression and it is a vector which depends on a single variable t. Okay, and t over here, it is a scalar. All right. If you are having maybe something like this, 2xi plus 3yj, then this one, again, it is a vector, but it depends on two scalars, x and y. So over here, we are having two variables, and over here, we are having a single variable. Okay, note over here, if you put t equal to 1, then you can have a different vector. If you put t equal to 2 in this expression, you will have another vector. Okay, so the expression depends on t. Similarly, over here, it depends on x and as well as the variable y. Okay, so that was actually an example of what we are going to have over here, but we must define it in a better way. Okay, so what will we do? And over here, the scalar that we will be doing will be real numbers. Maybe in your higher semesters, you will learn when the scalar variable, it can be a complex number. But over here, we will strictly be learning when the scalar is a real number. All right, so let us see. Let A be a set of real numbers. If you remember that when you have to define functions, you first of all need two sets. Okay, so over here, because we are needing a single variable, so that's why A will be a set of real numbers. And because we want a vector function, so let capital V be a set of vectors. Then I will write over here f from A to V, and over here, because I want to say that it should be a vector function, we will be writing f with an arrow. Again, some books, they simply write it as f but in bold. Okay, sometimes the books, they write it in bold, something like this, f from A to V. Okay, but over here we will be using the notation f with an arrowhead to denote that it is a vector function. So then f is a vector function if for all t belongs to A, for all t belongs to A, there exists a unique vector V belongs to capital V such that f bar t equal v bar. Over here, just take a note, because t, it is a scalar because it belongs to a, so it will be a real number which is a scalar. So I don't put this vector over t, okay, but I put the vector over f bar, t equal small v bar. Okay, so I will just give an example. Let's see. Example, I will take the set A. I will make it very simple, maybe 1, 2, 3. Maybe I will take V. Okay, V, let it be the set of all vectors. Okay, any vector that you can think of, okay, it will be in V of all vectors. Okay, then I will just define over here then f bar t equal ti plus maybe t squared j minus sine t k. Then this one, it will be a vector function on the set A, because as you can see, if you put t equal 1 over here, you are getting the vector 1i plus 1j minus sine of 1k. And if you put t equal 2, similarly you will be having a unique vector. And if you put t equal 3, you will be again having a unique vector. Okay, so this one is a vector function. On A. But over here, as you can see, the set A, it is 1, 2, 3, which is a set of real numbers. But if we have to discuss something about continuity, derivability, derivatives, okay, limits, then this set, okay, it won't do. Okay, it is not so interesting. So how will we make this set more interesting? It should be again a set of real numbers. So I will form maybe an example number 2, where A is the open interval 1, 2. Okay, again V is the set of all vectors. So over here, A, we are having an infinite set. Okay, whereas A over here, we are having only 3 elements. Over here, we are having so many elements, 1.5, 1.1, okay, 1.9, and all those numbers, they are in this interval. So again, we can define it with the same function, ti maybe minus tj plus k. Again, it will be a vector function, okay, on A. Then ft is a vector function on A. So over here, from now onwards, when we are discussing vector functions, we will be using intervals like this, open intervals, but instead of 1, 2, maybe we can have in general, I will write over here 3, a equal ab, where a is any real number and b is again any real number, v equals set of all vectors. Then the same thing, ti minus tj plus k is a vector function. Okay, so we have seen something that is a vector function. You have to be very careful, because some of them, they may appear like vector functions, but in fact they are not. Okay, I will give you an example of something that is not a vector function, even though it looks like a vector function. Okay, example of an expression maybe, which is not a vector function. Which is not a vector function. So over here again, I will take the set A, maybe okay, minus 1 1. I will take V again, set of all vectors. Okay, so over here, this one, f bar t equal 1 by ti plus tj plus tk. This one, it is not a vector function. It is not a vector function because if you put t equal to 0, then you are having 1 by 0, which is undefined. So this is when we say that it is not a vector function. It's not a vector function. Because f bar 0 is undefined. Okay, so even though it looks like a vector function, but it is not, because you will be dividing by 0 if you put t equal to 0. Because maybe I should write over here, when t equal to 0, f bar 0 is undefined. Okay, so you have to be very careful. You just have to see whether it's defined or not. If it is defined, then it will be a vector function. Okay, so over here you should be remember that there are different types of functions: constant functions, okay, polynomial functions. Similarly, over here we will have something, okay, but the most interesting that we will be studying, they are these type of functions. The first one is vector function which has constant vector functions. Number 2, okay, vector functions of constant magnitude. And number 3, vector functions of constant direction. Okay, let us just first see what is a constant vector function. Okay, a vector function is constant ft is constant if it does not depend on t. Okay, for example, I will just write over here, maybe f bar t I plus j minus k. So over here, even if you put t equal to 0, you will still be having the same vector. In fact, this does not depend on t, so it will be constant. Okay, even if you change t, you will still be getting the same vector. Okay, and over here, let us see vector functions of constant magnitude. A vector function ft is of constant magnitude if the magnitude of ft is constant. Example, okay, I will give an example for this one. Let us see. An example of this one will be something like this. Number 1, let us take ft equal I plus j. Okay, maybe 2i plus j. How much will you find if you find this magnitude, f bar t? F bar t, it will be root over 2 squared plus 1 squared, which is root over 5. So this magnitude, it does not depend on the vector t. So that is why ft will be okay, so this one is an example since this one does not depend on t. Okay, let us take a more interesting example. So over here you may think that because this one does not depend on t, So this one does not depend on t, that is clear. Okay, but sometimes we can have that this one over here depends on t, whereas the magnitude does not depend on t, as we will see in this example number 2. Let us take ft equal cos ti plus sin tj. So this one, it is not constant, right? It is not constant because it depends on the variable t. Compare this one with this one. This one, it is constant. Also, it has constant magnitude. This one, it is not constant, but this one, the magnitude, how much will be the magnitude of this one? Will be square root cos square t plus sine square t, which is equal to 1. Okay, so even though this vector is not constant, but we are finding that the magnitude, it will always be constant, not depend on t. Again, this example is very much useful, okay, as you will see later on when we are discussing in more detail about this type of vector functions with constant magnitude. Okay, so actually if you want to draw this one, how will we draw it? Okay, let us see. So over here we are having only the vector I and j, so that is why we can draw it in a two-dimensional plane. So over here what we will be having, we will be having these type of vectors. When you put t equal to 0, if you put t equal to 0, you will get cos 0i plus 0j. So you will be getting this vector. It starts from this point, it ends at this point. If you put t equal pi by 2, then you will be having this vector. If you put t equal 180 degree or pi, then we will be having this vector. Similarly, if you put t to be any angle, okay, we will be getting these type of vectors. So as you can see over here, the lengths of these vector, they are all equal. Okay, but you are having so many vectors, so that is why it depends on t, but their lengths, okay, even if you change t, the lengths will remain the same. Okay, so keep this example in mind. The third type of vector functions that we will be doing is vector functions of constant magnitude. Vector functions of constant direction. Okay, so I will define it. Is of constant direction if a vector function ft is of constant direction if remember that when we are talking about direction, we just need the unit vector. So that's why we will be writing it like this. If this one is constant, that is, this vector, it can be denoted by this unit vector. That is, if the unit vector is constant. Okay, so again, we will see an example. Okay, so let us just first look at it from the graph, okay, then maybe we can form an example. Okay, so this vector over here, 1i, it has length 1, but it is pointing along the x direction. Now take a look at this vector 2i. Again, it has the same direction, but different magnitude. Now take a look at this vector starting from here, ending up to here, 3i. Again, having the same direction, but different magnitude. Okay, so over here, what can we do? Okay, so I will write it like this. Example. Take f bar t equal ti. Okay, so if you put t equal 1, you will get 1i, t equal 2 equal 2i. Okay, so this one, it is of constant direction. But if you have to prove it, okay, again from the graph it looks clear, but if you want to prove it, then we will have to use this definition, because f cap t, which is equal to ft by magnitude ft. This one it will be equal, so ft will be ti. The magnitude will be root over t square. So if you simplify it, we'll be getting I, which does not depend on t. Okay, this is one example. Another example that you can give is something like this, which is ft equal I plus j. Okay, so this one, it is a constant vector, so that's why we'll also be having constant direction. Okay, maybe I should write that one as a note. A constant vector, constant vector function always have the same, always have a constant magnitude and constant direction. So this also will become very useful when we are doing some exercises and also some theorems that we will be proving. Okay, just keep it in mind. So now that we have seen the types of vector functions, let us just discuss briefly about limits. Limit of a vector function. The limit of a vector function ft at a point t equal t naught is a vector A. Okay, and it is a vector A such that, okay, if you remember in your first semester when you were dealing about limits of real valued functions, you were using epsilon and delta. Similarly, over here when we are talking about vector functions, we will be using epsilon and delta, such that for any epsilon greater than 0, there exists a delta greater than 0, so that ft minus a is less than epsilon whenever 0 less than t minus t naught less than delta. If such an A exists, then we write limit t tends to t naught ft equal A. Over here you should be very careful because we are having this symbol. Okay, this symbol can be used for the determinant, can be used for magnitude, can be used for modulus. But over here you should be very careful. Inside we are having vectors. Okay, so that is why this symbol over here it will be magnitude of vectors. Okay, and over here this symbol, inside we are having real numbers. T and T naught, they are real numbers, so that's why this one will be the modulus symbol. Similarly, you can call it magnitude, okay, but just to be more precise, we will call it the modulus symbol. Okay, so this is the definition. What exactly does it mean? Okay, it is very simple. Okay, let us see. Okay, I will give an example. Let us just take a look at this. Ft equal Ti. Okay, and T naught is equal to 1. Okay, so let us just first draw all these vectors. Okay, let us see. I hope I can explain it clearly by using this picture. So let us just draw these vectors. Okay, so F1, it will be 1i, so it will be somewhere over here. Okay, so this one will be F1. F2 will be this vector starting from 0 ending at this point. Okay, so F3 will be something like over here. But remember that because we are dealing with limits, we have, and we want to make T naught equal to 1. So T naught equal to 1 over here, T naught equal to 2. Okay, let us see. Because we are dealing with limits, we have to make it very, very close to this number. Okay, so instead of, we can find this vector when it approaches T naught equal to 1. Okay, so let us see. If we set T naught equal 0.99, okay, 0.99, we will see that F bar T, it will be 0.99i. Okay, and if you set it to be even more closer to 1, maybe T naught, sorry, if you set T equals 0.99, then F bar T will be this one. If you set T equals 0.999, okay, again it is very close, 0.999i. So based on this pattern, we can see that if T approaches T naught, which is 1, then F bar T approaches 1i. Okay, I can write down over here. If T approaches T naught equal to 1, then F bar T approaches the number 1i. Okay, so over here F bar T, it is this function. A bar, it is this. A bar will be this vector 1i. I hope that is clear. Okay, do not worry. Again, maybe I will explain later about the meaning of epsilon and delta. But for now, just take this one. Okay, this the value when these scalars approaches T naught. Okay, so the vector when the scalar approaches T naught, it is the limit of Ft. Okay, so let us see about continuity. Let Ft be a vector function. Of a single variable t, then Ft is continuous on t equal T naught if, so last time we were writing limit Ft equal to a, but over here if we want it to be continuous, then limit t tends to T naught, Ft should be equal to Ft naught. Okay, when we are doing examples, we will see. Okay, we will see of some continuous vector functions and some functions which are not continuous. Okay, if we want to write this one as a vector in terms of epsilon and delta, we can write that is for any given epsilon greater than 0, there exists a delta. This one is delta greater than 0, so that magnitude ft minus ft naught less than epsilon whenever 0 less than modulus t minus t naught less than delta. Okay, so this is the continuity. And remember, if you are saying limit, you have to say at which point. Similarly, if you say continuity, you will say continuous at which point. Okay, so just keep this in mind. Okay, and over here I will end with some very important theorems and limits. Okay, or maybe we can do it next time. Okay, next time we will do theorem on limits, as well as we will be discussing about derivatives.